All right, so acids and bases. Before we really knew what acids and bases are, we knew a couple things. So early chemists used to take chemicals in order to tell properties about them. This is one of the ways that the first amino acid was discovered. It was derived from asparagus. The amino acid is called asparagine. It tasted, this crystal of asparagine tasted different than other crystals. And the same sort of story applies with acids and bases. Chemists knew that acids taste sour and the bases taste bitter. Please don't taste anything you're not supposed to taste. But you probably are familiar with this. So here's a picture of some Sour Patch Kids. If you look at the ingredients, we've got citric acid. That's going to be giving you that tart flavor. There's also tartaric acid. That's going to play a role as well. There's lots of different compounds that give you the bitter taste. Does anyone in here know if they're a super taster? Anyone heard of super tasters? Yeah, they're really sensitive to the bitter taste. You can, my husband, I believe, he's either lying or he's a super taster. He claims to hate vegetables and chocolate and coffee. So that's basically what a super taster is. But they have a different number of taste buds. I think it's more taste buds than the average person. So someday he's going to be experimented upon. I'm going to count his taste buds. But anyway. Okay, so Svante Arrhenius was the first person to really determine what an acid and a base is, at least with a loose definition. So an Arrhenius acid is said to be a compound that produces hydrogen ions or hydronium ions, so H plus or H3O plus. Now, obviously, structurally, these are different, but we're going to use them interchangeably. They're both signifying an acid is formed. Okay, the H3O plus is simply water plus a proton. In an aqueous solution, that's how our proton is going to exist. We're going to be talking a lot about protons. So the Arrhenius base is something then that produces hydroxide, OH minus. The way Arrhenius came up with some of his concepts was he was doing a lot of work with dissolving substances and testing their for conductivity. And this is essentially one of the ways that pH meters came about. So pH meter is simply looking for conductivity. And Arrhenius also won the 1903 Nobel Prize for his work on electrolytic theory of dissociation. So this dissociation is important. When we put acids and bases in solution, we're going to see, in most cases, some amount of dissociation. And by the Arrhenius definition, that dissociation for an acid means that we're producing a proton. For a base, that means we're producing hydroxide. All right, so we can sort of look at an example here with hydrochloric acid. HCl is a strong acid, which means that it completely dissociates into H plus and Cl minus. And I've used a single arrow to designate complete dissociation. You're going to see this come up a lot. Okay. That means if you put HCl in water, you're not going to have any HCl left. You're only going to have H plus and Cl minus. The other way to write this is that HCl in water produces H3O plus and Cl minus. Okay. So these are essentially the same equation. One is a little faster to write, so sometimes I'll write H plus, the other HCl plus. Obviously, you need to have the water. Yes?
So you said since it completely dissociates, it's a strong acid?
Mm-hmm. Yeah, since it completely dissociates, it's a strong acid. That's the definition. Those are going to go hand in hand. So an Arrhenius base then is something that produces hydroxide in solution. Lithium hydroxide is a strong base. It's going to produce lithium ion and hydroxide ion. Unfortunately, the Arrhenius definition for acids and bases is really limiting. It's only going to work in aqueous solution, and if you progress in chemistry and you take organic, you'll find that there are acids and bases in organic solutions, so things that aren't taking place in water. And it only allows for one kind of base. It produces hydroxide. Okay? So this is really limiting. We need a new definition. And that's where the Bronsted-Lowry definition came into play. So what the Bronsted-Lowry definition says is that a Bronsted-Lowry acid donates a proton, and a Bronsted-Lowry base accepts a proton. And when we say proton, we mean H plus for the most part. We'll just stick with H plus. Okay. So Bronsted-Lowry acid donates a proton. Bronsted-Lowry base accepts a proton. So we can go back to our HCl example, where we have HCl in water forming H3O plus and Cl minus. And you can see that the proton from HCl is donated to H2O to form H3O plus. And so the Cl minus is left, and we're going to refer to this as a conjugate base. I'm going to come back to that in a second. So if water is accepting a proton, in this case, is it an acid or a base? It's a base, right? So Bronsted-Lowry base accepts a proton. So water is accepting a proton. And it's acting as a base. When an acid donates its proton, what's left, the Cl minus in this case, is the conjugate base. Okay? Conjugate acid-base pairs differ by one proton. I think I have this definition here in the next slide, but we can write it out. Conjugate acid-base pairs differ by one proton. And so what that means is that if water is acting as a base, then H3O plus is acting as the conjugate acid. All right. Does that make sense? You're going to get a lot of conjugate acid base questions in your essential skills. And essentially what we're looking for is differ by one proton, okay? HCl donates a proton, forms Cl minus, that's our conjugate base. All right, take a second and look at this example with ammonia. Ammonia, you may or may not remember. But take a look, figure out what the base is, what's acting as an acid, what's acting as a base, the conjugate acid and the conjugate base. Okay. If you take a look at the reaction that's shown, you'll notice that we have NH3 forming NH4 plus and H2O and OH minus. So water in this case is donating one of its protons to ammonia to form NH4 plus and leaving OH minus. Okay. So in this instance, water is donating its proton. So is it acting as an acid or base? Acid. And then in this instance, hydroxide ion, OH minus, is the conjugate base of water. It has one fewer proton than water. And NH4 plus is the conjugate acid of NH3. So the conjugate acid is always going to have one more proton than the base. Make sense? Yes?
When you say that NH3 is then the conjugate base of NH4?
You can say that if the reaction were written in reverse. So typically when we're naming, so we'll either say conjugate acid-base pairs, or we'll say that the thing on the product side is the conjugate of the thing on the reactant side. Any other questions? All right, so take a second here. What is the conjugate base of formic acid? It may help to write out an equilibrium to help you see this. So formic acid has the formula HCO2H. If you want to see a structure, I remember it, yes. Okay. So if you put formic acid in water, an acid is going to donate its proton, and we'll be left with H plus and what? Anyone want to offer a suggestion? A. Yep. HCO2 minus. HCO2 minus. And all of this would be aqueous. Got a little sloppy here. Okay. One thing. This is not a strong acid. Okay, so I don't need the single arrow. In fact, it's a weak acid. So with our weak acids, we're going to use double arrows to show that there's an equilibrium. More on that later. All right, what's the conjugate acid of H2PO4 minus? All right, H2PO4 minus, if you put it in solution in water, it's going to be in equilibrium. There's a couple of things that can happen, but we're looking for the conjugate acid. So that's going to be the species with one additional proton. So we're going to form H3PO4 plus OH minus. Okay. Does everyone see that one? Now, H2PO4 minus is a special type of ion. H3PO4 phosphoric acid is a polyprotic acid. H3PO4, if you put that in solution, you can form H2PO4 minus. H2PO4 minus can subsequently go on to lose a proton and form H plus HPO4 2 minus. It can lose a third proton and form PO4 3 minus. Okay, all aqueous. So it's one of those polyprotics. The other term that you're going to see for something like H2PO4 is amphiprotic. meaning it can either donate a proton or it can accept a proton. I think I changed this slide a little bit from what you have in your notes, so check the reaction. So I have HCl plus NH3 forming NH4 plus and Cl minus. And here everything is aqueous. We're going to imagine we're in aqueous solution. Is this an Arrhenius acid-base reaction? No. Why not? What's that? There's no OH minus, there's no H plus produced. So it's not an Arrhenius acid-base reaction. Is it a Bronsted-Lowry acid-base reaction? Yes. Or transferring protons. Okay. HCl is donating a proton to NH3. And of course, NH3 is accepting a proton. Okay. In this case, again, HCl acts as the acid. Ammonia is the base. NH4 plus, what's that? Conjugate acid or conjugate base? Conjugate acid, yes. And then Cl minus is our conjugate base. Unfortunately, Bronsted-Lowry definition is still a bit limiting. Okay? So we need one more definition, at least one more that we'll talk about in this course, and that is the Lewis acid-base definition. Of all the definitions, I think this one might be the most challenging to wrap your brain around, and that's because we're not looking at something like a proton moving, we're actually looking at electrons moving. So a Lewis acid forms a covalent bond by accepting an electron pair. And a Lewis base forms a covalent bond by donating an electron pair. I'm going to use E minus for electron. Okay, so Bronsted-Lowry, we're talking about protons. Here with our Lewis definition, we're going to be more concerned with the electron. And this allows us to look at transition metals and how they can behave as acids and bases. And that's not really possible with our Lewis definition or our Arrhenius definition. So let's go back to our reaction of ammonia and hydrochloric acid. You guys remember drawing Lewis structures? All right, so let's draw the Lewis structures of NH3. And let's also draw the Lewis structures for, and let's put HCl in solution, strong acid, so H plus and Cl minus. Okay, so imagine that has dissociated, now you have H plus and Cl minus. So you've got three things to draw the Lewis structures for: ammonia, proton, chloride. I'll take a couple seconds here. Feel free to talk with your neighbor. You guys remember doing your Lewis dot structures? All right, so I have the outline here of our Lewis dot structures. So our ammonia should have a lone pair on the nitrogen. And the reason we're drawing these Lewis dot structures is so we can see where there are extra electrons, or lone pair electrons, not extra. Proton, simply a proton, no electrons. Okay, chloride ion. It's going to have 8 electrons. All right, so we said a Lewis acid accepts an electron. I always like to remind myself, Lewis acid accepts. Lewis base donates. Oops. Okay. So what's going to happen here? We have to form a nitrogen-hydrogen bond. We'll say it's this one. And so in order to do that, we're going to take our lone pair. Ammonia, NH3, is going to donate its lone pair to the hydrogen, or the proton, to form that bond. Okay. So we knew from our Bronsted-Lowry definition that ammonia was a base. We know the proton is going to act as an acid. So we're verifying with our Lewis dot structures and by looking at the Lewis definition that yes, this acid is accepting a pair of electrons from the nitrogen and ammonia to form that bond. And so we've got our Lewis definition. Okay. You guys see that? Okay, so this kicks it up a notch. All right, so I'm going to zoom in on this figure. So we have, I know this is small, so we have iron. It's coordinated with water. There's 6 water molecules coordinated with this iron. So center atom here is iron. We have our water molecules coordinated to the iron. And so there's 6 of them located around the center of the irons. We have an octahedral complex. So what's going to happen in water? So take this iron hydride and put it in water. And a water molecule from the solvent is going to interact with one of the hydrogens on a water that's coordinated to the iron. And what that's going to do is weaken the OH bond that's coordinated to the iron, and we'll form H3O+. And then we'll have, in terms of the iron complex, iron with 5 water, 1 hydroxide, and because of the OH minus, we're actually going to end up changing the charge to a 2+. Okay? Key points here: water in solution can grab one of the protons from the coordinated complex and form an acid. Okay? If you draw out the Lewis structures for this, what you'll find is this is a Lewis acid, Lewis base interaction. Okay? One thing that's important to note, there are a number of different metals that will do this. This isn't a complete list of cations, metal cations that'll do this. Take a look at your transition metals. Pretty much anything could potentially act as a Lewis acid with different amounts of strength. But one of the key factors is that the magnitude of the charge. So the greater the magnitude of the charge, the greater the chance of of that cation acting as a Lewis acid accepts Lewis acid. Right? No. Yeah. Okay. So, cations with a large charge are strongly attracted to water molecules, and they act as Lewis acids. Right? This section in your book, I think, is actually 16. It's later in the chapter. I don't know why it's separated from everything else, but it is later in the chapter compared to the other definitions for acids and bases. Questions on this? All right. For now, let's focus more so on our Bronsted-Lowry definition. Here's our summary slide as well. So the three different definitions, again, with Arrhenius, very limiting. You've got to have a proton or hydroxide for acid or base, respectively. Bronsted-Lowry, we're talking about accepting and donating protons. And then Lewis acids and bases, we're talking about accepting and donating electrons. Okay? For those Lewis acids and Lewis bases, you really want to write out your Lewis dot structures. Same Lewis, by the way. Probably figured that out. Okay. So you do need to memorize your list of strong acids and strong bases. The main reason is when you encounter acid-base problems on homework or exam or whatever, strong acid, strong base problems are typically much easier to solve than the weak acid, weak base. So if you can recognize all of your strong acids and your strong bases, you'll know that you have what type of problem you have. Okay? And typically, like I said, they're easier. One of the things we sort of mentioned before is that with our strong acids and strong bases, we use the single arrow to denote that the reaction occurs to completion. And that's our dissociation reaction. The other thing to note, and again, our essential skills should pound this into your brain. With calcium hydroxide, strontium hydroxide, and barium hydroxide, for every one of these molecules, you're going to form 2 hydroxide. Okay? So if you take a 1 molar solution of calcium hydroxide, and you want to count the OH minus, you're going to have twice the number. So 1 molar solution of calcium hydroxide is going to be 2 molar in OH minus. Okay? We're going to try to pound that into your brain. So that's an easy way to make a mistake on an exam. Right. Yes?
The same for hydrogen sulfate,
For sulfuric acid? No, I'm glad you mentioned it. Okay, so this one gets an asterisk. The first proton leaving H2SO4 is strong. H2SO4 in water will form H plus HSO4 minus. But HSO4 minus is a weak acid. Okay? So HSO4 minus will have equilibrium arrows with H plus and SO4 2 minus. So honestly, you typically don't see too many problems with sulfuric acid because of this complication. Should you encounter one, I would say, depending on the question, it's most likely that it's asking for sulfuric acid as a strong acid, but there's probably like a 3%, I like making up numbers, 3% chance that's not true. So we'll go with that. Okay, but yeah, main thing, first proton leaving, strong, single arrow. Second proton leaving, weak, double arrow. Yeah, okay, so chloric.
It says chloric is also
Hmm.
liquid for chloric acid.
Interesting. Let me check on that. If that's in chapter 4, we'll go with it. Yeah, let me see. There's a chance that it has a Ka associated with it, equilibrium associated with it. It's just really big. So let me take a look, because I haven't seen that one. Okay. All right, so I believe this table is from your textbook. So this lists some strong acids, not all, and several weak acids, not all, and OH minus, H2, and CH4. So let me get to that in a minute. So the way that these are listed is if you go down the table in order of decreasing acid strength. So our strong acids are at the top, our weaker acids are at the bottom. Okay, I guess the arrow shows upward. Hello. Acid strength increasing, going up. Again, fully dissociate with those strong acids, use the single arrow. Weak acids do not completely dissociate, use the double arrow. OH minus, though it has a proton, really doesn't dissociate very easily in water. Yes?
The book also says chloric acid is a strong acid.
My stuff, so. Huh, interesting. Here, whoops. We'll look at our acid strength. Here's our H3O plus and our CH3, our acetic acid, CH3COOH. We'll notice that H3O plus is the, okay. So then the other half of this table shows you the conjugate bases of the acids that are shown. So for instance, we talked about HCl, the conjugate base being Cl minus. HSO4 minus, conjugate base being SO4 2 minus, and so on. You'll notice that the base strength increases as you go down the table, so it's opposite. Okay? A strong acid is going to produce a very weak conjugate base. And so much so that the strong acids, we use that single arrow to say that you don't even have to consider the possibility that these could react with water to form a base, to form OH minus. Okay? Something like fluoride ion, the conjugate base of HF. Okay? HF, F minus fluoride ion can react with water to reform HF and OH minus. Okay? As we go down the table, the likelihood of this hydrolysis reaction occurring with these various ions increases. Okay? And we're going to talk more about this. We're going to apply some numbers to this. Okay, we're going to look at equilibrium values associated with these types of equilibria. All right? But I just want you to get a sense for what that means with this table. Stronger acid. Can I say it anymore? Strong arrow, or strong acid, single arrow. Okay. Yeah, this basically just repeats what I told you on that table. So HI, because the conjugate base of HI is I minus, because that conjugate base is the conjugate from a strong acid, it is very unlikely to react with water. The other thing So it's a very, very, very weak base. We wouldn't even consider that being a thing that could happen. The other important thing to note is that an acid favors the side of the reaction with the weaker acid. And what I mean by favors the side is that there will be more either reactants or products at equilibrium. So H3O plus in this example is the weaker acid. And so there are going to be more products than reactants at equilibrium. And I know I said this has a single arrow. We don't really need to consider an equilibrium. That's what I'm trying to show. Okay, so if we had an equilibrium, we would still favor the side with the weaker acid. All right. Does that make sense? Okay. Acid. So our weak acids don't completely ionize in solution. They don't completely dissociate. So here is, second slide. Here's acetic acid. We put it in solution. It forms acetate ion, CH3COO-, and H3O+. So the acetic acid donates a proton to water, forms the conjugate base, acetate ion. Yeah, okay, I gave you all the clues here on the and H3O+, the conjugate acid. So again, acetic acid acts as our acid. Water in this case acts as a base. Acetate ion is the conjugate base, and H3O+ is the conjugate acid. If we go back to the table, okay, so H3O+ is the stronger acid, which means that our equilibrium favors the side with the weaker acid. So we expect this reaction to be reactant favored, there be more reactants in solution. And so if you were to take acetic acid and put some of it in solution, I think I have some actual numbers here. 0.1 molar acetic acid, 0.1 molar acetic acid, and you put that in solution. Only 1% approximately of acetate ion is formed. So only 1% of the acetic acid dissociates to form acetate. So it is a very small amount. We're going to work on these types of calculations here soon. The other thing that's kind of good practice is to be thinking about what an acid, strong acid, or weak acid, or strong base or weak base looks like in solution. Okay? So we have two bottles here. One contains a strong acid and the other contains a weak acid. In both cases, the acid is represented by HA. Okay, so HA, H being the proton, A being any acid. Okay. With our strong acid, HA in water forms A- and H3O+, single arrow. Okay, completely dissociates. And so if you look at what's in the magnifying glass, we don't find any HA molecules present. Okay, there's only A- and H3O+. On the side with the weak acid, in this case we have HA plus water in equilibrium with A- and H3O+. Now, not only do we have A- and H3O+ in solution, but we also have HA. We have undissociated weak acid in solution. And in fact, there's a lot of that. So 1, 2, 3, 4, 5, 6, 7 of those. 1 A-, 1 H3O+. Okay. So when you're thinking about strong acids and weak acids, I want you to be thinking about these pictures. Small amounts of dissociation with our weak acids. The way that we describe weak acids is with our an acid dissociation constant. Okay. We call that Ka. Ka in this case is an equilibrium constant, just like K from chapter 15. The small a just represents acid. You'll notice, and at least with this list of acids, that these acids are listed for stronger acids at the top and weaker acids at the bottom. Strong acid, our Ka is 1 times 10 to the minus 2. So this is chlorous acid, HClO2. If HClO4 is a strong acid, this is a pretty big Ka, so HClO3 is going to have a bigger Ka than this. I'm wondering if that table you're referring to is just simply saying that's a strong acid. Maybe. Any case, really weak acids are going to have very small values of Ka. The bottom one here is 10 to the minus 10, okay, for phenol. You do not need to memorize any Kas. Really, the only acid you should probably have memorized for the exam is acetic acid. Okay? Not the Ka necessarily, just be able to recognize that that is a weak acid. Okay, so I mentioned phosphoric acid being a polyprotic acid, or triprotic acid to be more specific. Diprotic acids have 2 protons that they can donate to solution. We talked about the dissociation of H2SO4 to H plus and HSO4 minus. And then HSO4 minus can subsequently have an equilibrium with H plus and SO4 2 minus. There are other diprotic acids, there's a decent number of them. The first deprotonation, whether it's a sulfuric acid or not, is always the stronger deprotonation. It has a larger Ka value. The second deprotonation doesn't happen as extensively. So if we look at an example for oxalic acid, it has two protons. We can abbreviate it as H2A, where A is our purple circle here, our 2 hydrogens are the white circles. The first deprotonation, the first Ka is 5.6 times 10 to the minus 2. The second one is 5.1 times 10 to the minus 5. So again, it gets smaller with the subsequent deprotonation. If you were to take a small number of molecules and put them in solution, I think I have approximately 56 molecules drawn here, you would find that even with a relatively large Ka value of times 10 to the minus 2, that only a very small fraction of oxalic acid would deprotonate one time. And then even smaller fraction, couldn't draw it, it's 1/10 of 1, it's 0.1, okay, would deprotonate a second time to get the fully deprotonated version. So it's kind of important to be thinking, well, we probably won't do many problems where we're trying to figure out the full extent of deprotonation for polyprotic, but it is kind of interesting to think about. Okay, strong bases, again, strong bases completely ionized, make sure you know the list. Again, the direction the reaction favors is towards the weaker base, just like it was for the weaker acid. OH minus is one of the strongest bases. So there are others that were, for example, on that table with the arrows that I showed you, but we likely won't see those bases. So just concern yourself with OH minus. All right. So here's our example with ammonia. Ammonia is a weak base. Reacts with water. It's going to act as an acid to form our conjugate acid, ammonium and OH minus, which is the conjugate base. In a reaction like this, if you see OH minus, you know that's the conjugate base of water. Now, water does a really cool and important thing. It automatically ionizes with itself, basically. So this is referred to as the auto-ionization of water. When you have water in solution, what you'll form, or what you'll find an equilibrium for, is H3O plus and OH minus. Okay? So let's finally write an equilibrium expression. Right? Let's jot down the equilibrium expression for the auto-ionization of water. So that is K equals what? Take a second, look at the equilibrium. Okay. So you'll find that when you write the equilibrium expression for the auto-ionization of water, you can ignore the reactants because they are liquids, right? So it's going to be products, which is H3O plus times OH minus. All right. And we give this K value a special designation. It's K sub W for the equilibrium constant for water. One thing to note is that this is temperature dependent. Okay. If you're working problems and it doesn't state the temperature, just assume it is at 25 degrees Celsius. Okay. And at 25 degrees Celsius, Kw is equal to 1 times 10 to the minus 14. Given the size of Kw, is this equilibrium reactant favored or product favored? Reactant favored, right. Small Kw, reactant favored. Which also means, and you may have guessed this, that you pour yourself a glass of water, it's mostly H2O, very little H3O plus, and very little OH minus. So let's calculate, this will be the last thing we do. Let's calculate the concentration of H3O plus at 25 degrees Celsius. So we know that our Kw at this temperature is 1 times 10 to the minus 14, and that this is equal to H3O plus OH minus. But we're not given any initial concentrations, right? So we can use an ice table. Initially, we can ignore our concentrations of water in the liquid phase, or liquids. We have no H3O plus, no OH minus. We know that as the reaction proceeds, we're going to form some amount X of products, H3O plus and OH minus, both with a stoichiometric coefficient of 1. So that at equilibrium, the concentration of H3O plus is X, which is equal to the concentration of OH minus, which is also X. So we can plug this into our equilibrium constant expression. We'll have X times X equals 1 times 10 to the minus 14. So take the square root of both sides, and we'll end up with X is equal to concentration of H3O plus equal to OH minus, which is equal to 1 times 10 to the minus 7 molar. All right, questions on anything?